Thank you so much for having me today. And thanks, Angie. I'm a Container Camp All-Star. That sounds pretty good. It's the next line on my resume after Docker Security Lead is Container Camp All-Star. Perfect. So thank you so much for being here today. As Angie said, my name is Diogo Mónica. I lead the security team at a company called Docker. And before I go to my talk, we'd just like to see a show of hands to see if people are awake. Who's using Docker in the audience? And who is using computers? Computers, just computers, general computers? Okay, the exact same people that are using Docker, which is a great way to understand that people are awake. So it's been great. This technology has been changing a lot, and I'm really excited today about talk about orchestrating least privilege. And I know this is a mouthful. So why are we here today? The main reason why we're here today is because the way that we deploy and create applications has been fundamentally changing over the past 15 years. You've probably seen an equivalent to this picture in every single slide deck that talks about microservices. But the reality is that we've went from monoliths to service-oriented architectures to now microservices. And we've realized that our applications now are composed by a multitude, in some cases of some companies, thousands of different independent services that have to all work in synchronicity to actually achieve the ultimate goal of the business logic of your application. And so now the main problem is that we have so many of these things that we have to somehow manage them, monitor them, and orchestrate them. And so today, I want to talk about orchestrating least privilege. But before I talk about orchestrating least privilege, I should probably tell you what is an orchestrator, right? And before I tell you what is an orchestrator, maybe I should tell you what is an orchestra first. OK, let's go to an orchestra. What is an orchestra? An orchestra is effectively a group of musicians. Each of them have their own role, and they're playing a tune, some kind of music, in this case, classical music, in synchronicity. The interesting thing about an orchestra is that there's a specific sheet music that they follow. And each of the musicians has their own sheet music, and they're following along. So in an orchestra, we have a couple of different components and a couple of different roles. The first one is you actually have the composer. In this case, this example, you have Bach, that creates a sheet music of a particular orchestra or a particular orchestration that you would like to actually be played out. The second person that is really important is you have an actual composer. Sorry, you have an actual composer. So you have somebody that is actually running the actual orchestra. And the final is you actually have a musician that is finally operating the actual music. And there's a lot of different musicians with a lot of different roles. So if we bring this back to computer science, we have the exact same thing. Instead of a composer, in this case, the previous example, Bach, you actually have you, the engineer, that writes a spec of exactly what you want to see running or playing on your servers. Instead of a conductor, we have an orchestrator, which is going to be the piece of software that is going to ensure that every single piece of your infrastructure is effectively in tune, in synchronicity, and creating the final application. And then you have, instead of musicians, your servers themselves that are playing the tune, in this case, actually running your applications. So if we continue with this analogy further, the four main things that a conductor, the person that is in front of the musicians, has to do are the following. Number one, it has to choose the musicians. Who is the tuba player? Who is the drums player? So it has to actually do the casting. The second thing is actually it has to assign the sheet music to each individual one of the musicians. There might be two different tuba pieces, and each of them are going to have their sheet music. And all of these components and these sheet musics are actually come together to actually compose the orchestra itself. In the third place, we actually have that the job of a conductor is to unify the performance. People have to start at exactly the moments that they should and play together. If they were playing individually, this would be jazz. It wouldn't be an orchestra. And the final thing, the job of a conductor, which is the thing that he's doing when he's waving his arms around, is actually setting the tempo. So it has to follow exactly what the composer wrote in the sheet music, but it gets to control the tempo and when things start and how things are played. So if we go back to our example of computer science, we actually have that the job of an orchestrator also is composed of four main things. Number one, node management. Instead of choosing the musicians, our orchestrator is going to have to choose which nodes are going to participate in this orchestra. Instead of actually doing sheet music assignment, Our orchestrators actually assign which tasks are going to be running on which nodes, such that our application is finally going to run. It is going to also do cluster state reconciliation. So the unification of the performance, in our case, is ensure that if a musician doesn't show up, or in this case, a server doesn't show up to work, there's some other server or some other musician that is going to take the load of that component of the orchestra. And the final component, obviously, resource management. Instead of actually setting the tempo, it ensures that everything that is running on your orchestrator and on your platform is running in the most resource-efficient manner. OK, so now that we know what an orchestrator is, I guess the next question, and it goes to the title of the presentation, is what is a least privilege orchestrator? But before I go into least privilege orchestrators, I should probably define what is least privilege. So what is least privilege? Least privilege is effectively the concept of specialization. Going back to our orchestration analogy, least privilege is the tuba player. The tuba player only has access to the tuba. It does not have access to the drums. The tuba player only has access to the sheet music to play the tuba. It does not have access to the sheet music to play the drums. And so if we bring this back to computer science, we have that the principle of least privilege is a process only being able to access the information and resources that are necessary for its legitimate purpose. No more, no less. And if we apply this to orchestrators, we finally get what a least privilege orchestrator is, which is an orchestrator that follows this principle of least privilege in the strictest manner possible. OK? So now, the obvious question is, we know what a least privilege orchestration is. Why do we actually need it? Why is least privilege a good thing, a thing that we want to achieve? It sounds like a lot of work. Well, it really comes down to which attacker models you're considering for your infrastructure. And so it's really important to consider the best attacker models and to design your architecture in a way that you can resist against the strictest attacker that you have in mind. And so let's go through 5 different attacker models that are all good to think about and that least privilege is going to help you with. The first one is the external attacker. If we go to our orchestra analogy, an external attacker and an orchestra is effectively somebody in the audience that does not like the current music and just throws a tomato to the actual musicians. In computer science, an external attacker is an individual that is outside of your firewall trying to get into your internal network. Easy enough. So now let's talk about an insider attacker. What does that look like? Well, in an orchestra, it's effectively a dog that has control over your actual music and actually volume and all the things in the back end. If we come back to computer science, an internal attacker is somebody that actually already has access to your internal network. So it is on the same side of the firewall. If we continue with these model of attackers, we have the third one, which I call the NSA cat. What does the NSA cat do? It listens on everything. So it has the ability of listening on every single piece of fiber or communication wire that you have. So it is what we call a passive attacker or a passive listener attacker. We continue this, and we now have our fourth attacker model, which is a malicious musician. You have a musician in your orchestra that is clearly not like everybody else. It is doing whatever it wants instead of doing whatever you want. In computer science, what that is you have a cluster where one of your nodes is compromised. Not one of your privileged nodes, but one of the nodes that is running the tasks is completely under control of an attacker. That's our fourth attacker model. And our fifth attacker model is the single hardest attacker model to defend against. Instead of having a worker that is unprivileged that got compromised, you now have the conductor itself. So you're trying to play an orchestra. And the thing that is moving the arms, it is absolutely random. This, in computer science, is a malicious manager or a malicious privileged node. The orchestrator itself got compromised. So these are our 5 attacker models that we want to protect against and that least privilege are going to help us reason about. So now the question is, OK, cool. Good way of reasoning about these attacker models. How far are the orchestrators in the world right now from actually meeting all these 5 attacker models? Well, my answer to you is orchestrators right now are street performers. They play the drums, they play the tuba, they play the violin, they play everything at the same time. They're incredibly entertaining. They're worth the $5 that you leave on the floor for them to continue playing, but it's really not what you want to run in a production environment from a security perspective, because everybody has access to everything. They are most definitely not least privilege. And so now the question becomes, OK, I understand that right now we're not there. I understand where we want to go, but how do we get there? And so for the 5 attacker models, there are 5 big things that we have to think about. Number one, if you want to mitigate an external attacker, so somebody throwing tomatoes to your musicians, number one thing that we have to do is we have to think about whitelisting access instead of blacklisting access. Blacklisting access is what we've been doing for the past 25 years with firewalls. Whitelisting access means that when you're creating an application, you explicitly say what this application is going to listen on, expose to, and from that moment on, everything else is effectively inaccessible. This protects you against somebody just throwing tomatoes at you. The second component, if you want to protect against somebody that is inside of your firewall, inside of your network, well, now it becomes really interesting because you actually have to have deep and granular authorization. It not only should be enough for you to be able to send an actual request, API request to my service. Your service should be able to authorize and authenticate every single thing inside of your network to try to say that, oh, I can only access the payment service from the web front end, and nobody else has access to this particular API. So granular authorization protects you against an internal attacker. If we continue and now start thinking about the NSA cat that can listen on everything on the wire, well, the reality is that if you define as an engineer an application and you tell an application to connect to another application, you should have to do exactly nothing for that communication between, in this case, your Rails application and your MySQL database for it to be encrypted. So everything on the wire has to be encrypted because otherwise NSA cat will just listen to all of your packets. If we now go to the actual worker, so we have our gorilla that is part of your orchestra. Well, this requires a different design from an orchestration perspective. Workers should not be able to have privilege over your orchestrator and pull resources. So you should not have a server be able to say, oh, I want this secret, and I want this application to run. It should be push. The managers and the actual privileged nodes that are orchestrating your environment should be able to say, no, this is exactly what you need to operate and nothing else. They shouldn't even expose themselves to being requested by the actual workers. And the final one, the mitigation of the malicious manager, so we have like our random conductor that is doing whatever it wants. Well, the only solution for this one is really going down further the signed spec route, in which you, as an engineer, sign what you want to happen. And you have the musicians not even trust the conductor and always validate the signatures directly from the engineer. So the only way to protect against this attacker model is to completely remove all trust on the orchestrator itself. And even though the orchestrator gets to make some orchestration decisions, it does not get to decide what is running where, by whom, with what resources. So this is really important. And so this brings us to something that my team has been working on for a while, which is our own orchestrator that we created at Docker, and we launched about a year ago, Swarm. I want to mention 2 things in Swarm that are particularly interesting and that follow this exact model of least privilege and of achieving what we want, which is the full protection against the 5 attacker models. So the first component is when you start a Swarm cluster, immediately you get a certificate authority automatically generated for you. So the first node that comes up generates a certificate authority and signs its own TLS certificates. And then from the moment on, every node that joins your cluster gets automatically assigned a cryptographic node identity, a TLS certificate that also gets automatically rotated for you. In this TLS certificate, it is then what is going to be used to identify whether you're a privileged node, a manager, or a non-privileged node, a worker, and is going to be used for mutual TLS between every single node in the cluster. The coolest part about this is that all of this mutual TLS infrastructure, the CA generation, the communication being encrypted and authorized and authenticated, comes on by default. You can't actually disable it. When you do Docker swarm init, just that simple command, automatically all of it gets generated for you. You have certificates being automatically rotated. You could actually bring down the rotation period of a certificate to 1 hour. So if you have 100 nodes in your cluster, every hour, every single one of your 100 nodes is rotating the TLS certificate. The reason why this is important is because it limits the exposure of having one of your certificate keys actually being shared to the outside, put on GitHub, or leaked to some paste bin somewhere. On average, you have 30 minutes of usefulness of that particular certificate. So that's the first component. We get you a way of disseminating content in a trusted way. And now that we have an infrastructure that has workers that are trustworthy, that are least privileged, and they get their own certificates, and managers that are communicating with each other with mutual TLS, we can finally actually have component security and infrastructure security that is enough to do secure secrets management. The reason why this is so important is because if you don't have the infrastructure built from the ground up, then your secrets management are actually not secret in a few different ways. Number one, when you do secrets management with Swarm, we automatically do encryption at rest. So automatically, all secrets are always hitting disk encrypted. They're stored in a Raft store on the manager nodes of Swarm, which means they're actually highly available because they're replicated across all the managers. And then the most important part is that if you have a red container running on a worker, then that container or that node will only get the secrets that it needs to run the red container. If you have another worker which is running a black container, then that other worker will only get the secrets needed for running that particular container. And then the middle worker does not require any secrets because we don't have secrets for the green container, and so gets access to nothing. The reason why this is so important is because this follows the principle of least privilege. Each node only has access to exactly what it needs to do its job, and it cannot request anything else. So this is really important. The other thing is this is really easy. As I mentioned in the mutual TLS case, this comes all on by default. You can't disable it. The encryption is there, the secure storage is there, the least privilege is there. The moment a container gets removed from a node, we also remove the secret from memory, such that if an attacker compromises the node, it can no longer access those particular secrets. So it's also least privilege in that way. And everything is behind a super easy interface. Docker secret create, Docker secret ls, Docker service create, and you have your secrets in memory, exposed as files, never get written to disk in a least privilege manner. So if I had to say what the current status of Swarm is, we are not a street musician or a street performer. We're like a jazz band. We actually have least privilege on the workers, but every single one of the musicians plays for itself. There's no centralized, trusted authority or conductor. And what we're trying to get to is obviously a full-on classical orchestra, where nothing is trusted, and even the conductor is and can be compromised. And for this, we would love to have your help. Thank you very much.